Unlocking innovation in the heart of the Midwest, where groundbreaking ideas meet state-of-the-art facilities. Join us in shaping the future of aerospace and technology. Introducing the AFRL Regional Network Midwest.
My name is Carlos Cal. I'm the CEO and founder of HySonic Technologies, a proud Purdue startup that has been awarded a Phase 1 contract from the AFRL Regional Hub. The philosophy of what we do at HySonic focuses on wave control. The company has been involved in external flow control, so controlling waves that naturally occur on the external shell of a hypersonic vehicle. And these waves are typically in the range of 100,000 to a megahertz. So very high frequency waves, but we've also been applying the same philosophy, same tools, same skill set to internal flow control, specifically in the propulsion system of hypersonic vehicles. The AFRL Regional Hub is interested in advancing the TRL level of our technology as it pertains to external flow control. To do that, in the first 6 months of funding, the first part of our effort will be extending the ultrasonic benchtop testing capabilities that Carl Jantze developed.
Hello, I'm Carl Jantze. I'm the PI for this AFRL Hub Award. Here we have our vacuum chamber at HySonic Technologies. This is the same vacuum chamber we use to evaluate the absorption characteristics of different material samples that are used to be flow control samples. By subjecting the sample in the vacuum chamber, we can control the pressure in the environment. We can also control the gas that we're using. In this case, we're using ultra-dry air. This allows us to simulate different altitudes and different acoustic characteristics that would occur at those altitudes. By placing the sample in the vacuum chamber in a certain setup and angling 2 ultrasonic probes, we can subject the sample to ultrasonic waveforms. Then we can extract the data in post-processing, evaluate what its absorption characteristics are. This allows us to evaluate what materials would be best for absorbing the acoustic energy that generates early laminar to turbulent transition for hypersonic flow.
Once Carl is done improving the testing, benchtop testing capabilities and helping us pick what material is best suited for wind tunnel testing, we ship that material to the Air Force research labs. And in the first part of the effort, they will test it on our old testing platform called the Boat, which is a small flat plate testing apparatus. But under AFRL Hub regional funding, we were able to design a new model, roughly this much bigger, with more real estate, allowing to investigate things beyond just aerodynamic flow control, significantly increase the TRL level of our technology, and also strengthen the partnership with the Air Force research labs, who are very interested and excited about this technology, which has already been proven successful.
In terms of results, you'll see that there is a plot of an acoustic absorption coefficient for this material sample against pressure. What you're seeing here is the acoustic absorption coefficient for this sample between pressures of 10,000 Pascal to 80,000 Pascal. And you'll notice, based on the red dots, that its performance is declining as we approach higher and higher pressures. What this means is that this material sample in particular will perform better at a higher altitude. The formula that you see here, beta, that is the acoustic absorption coefficient. It's marked out by 1 minus the ratio of the porous amplitude in comparison to the reference amplitude squared. So when we take these tests, we measure our porous sample, we measure a reference, and we compare those amplitudes together at each individual pressure that we're interested in. This allows us to get that curve in the pressure domain.
Okay, so this is the model that we've been testing in the wind tunnel. We've got a steel leading edge out front, and then this material is made out of a PEEK material, which is good with our IR camera. All of these holes are for different PCB pressure sensors, and then this cavity right here is where we would put the porous insert. You can see there are the PCB holes on this side as well, and there are matching PCB holes in that insert. And then we'd like to have it kind of this way, almost the insert right next to this PEEK non-porous area, so we can do a side-by-side comparison between what the boundary layer is doing with the PEEK material versus with that porous insert.
I'm Dr. Running. I'm an assistant professor here at the University of Dayton, and for this project I've been helping along with Megan lead the charge with the design of the model, the testing at Wright-Patterson Air Force Base in their Mach 6 Ludwig tube, and then post-processing, analyzing the data, and planning for future tests. All right, so here's some very fresh, very preliminary data. Basically what we see here is just an image from top down of our large flat plate model. And the different colors are representative of heat flux, which you can kind of think of as an energy source, temperature, into our model. So we would like to reduce heating with our porous materials. That's our goal of the project, is to reduce the heating due to the porous materials effects on the boundary layer. And so this kind of gives us a global picture. This data was taken from above during a wind tunnel test with an infrared camera. And then if we take a profile along a particular ray along this large wind tunnel model, we get a bit more quantitative data here, and we see this reduction as we're moving downstream of heating, and then we see an abrupt increase in heating, and this abrupt increase in heating is indicative of the initiation or start of transition of our boundary layer state from laminar to turbulent. And so this is the sort of thing that we're trying to measure, and then this is the sort of thing, this boundary layer transition, that we're trying to control passively with our novel porous materials.
Okay, so this is a spectra plot with data taken from the PCB pressure sensors that were those little dots that we showed you in the model. The y-axis, that is kind of the amplitude of what we were reading versus the frequency. And you can see right here, these two peaks, the kind of pink and blue colors. Those are indicative of the instability that we specifically are looking at, the second mode instability. And we're hoping that with the porous materials, these peaks will decrease in amplitude. It'll dampen out kind of those peaks that are indicative of that second mode frequency.
So in this first 6 months of work, we've achieved two very important milestones. Milestone number one is improved benchtop testing capabilities. This is a testing apparatus that Carl developed back in 2019 under ONR Phase 1 funding. And under regional, AFRL regional funding, he had the opportunity to extend the pressure range in which he can do these ultrasonic testing, and the ultrasonic frequency range at which he can assess material properties. So this was a milestone number one. Now, milestone number two is we've designed a brand new wind tunnel test article called the Aircraft Carrier. It's a big article, a lot of real estate to do a lot of different testing. And we've successfully gone through one wind tunnel test entry where we've provided the proof of concept that indeed we can design this test article to achieve hypersonic transition at different locations at different distances from the leading edge. And moving on to the incremental phase of the funding for the following 6 months, we look forward to testing different materials with different recipes that achieve different types of surface porosity, and that will cover a wide range of parameter space in terms of material design and aerodynamic conditions that can allow us to inform control strategies for hypersonic vehicles at various altitudes, hence different Reynolds numbers, and achieve the overarching goal of this effort, which is reduce hypersonic boundary layer drag.